Okay, hi everyone. The first thing I want to talk about are rings. Rings are kind of the basis of everything in number theory. It's just a type of number system. You're very familiar with them. You just may not have heard the term before. So for example, consider the integers. Remember, this is written as a Blackboard bold Z, like that. Comes from Zahlen, the German word for number. Something like that. That makes you a little better. And it's a set, right? It's a set. It has two operations, plus and times. And what do you know about those operations? Well, they're closed. Maybe I'll just put that here. Meaning if you add two integers, you get an integer. If you multiply two integers, you get an integer. Order and grouping doesn't matter. So like you can add in any order, multiply in any order. You can group, you can add, if you have three things to add, you can add the first two, then the third, you can add the first and the second, you can add the second, third, then the first. Multiplication distributes over addition. That's important. What else? There are additive and multiplicative identities. So we have, there exists 0 and 1, multiplicative additive identities. And there are additive inverses. Notice there are not multiplicative inverses. So I'll say additive inverses, but not necessarily multiplicative inverses. So 2 does not have a multiplicative inverse that also lives inside the integers, right? 2 has a multiplicative inverse called 1/2, but that's not an integer. But not necessarily multiplicative inverses. And it turns out that anything that satisfies all of these properties is called a ring. So such number systems are called rings. So the axiomatic definition is the following. Let me just write this out sort of more nicely. So a ring, but you should think of the integers in your head as the avatar for rings. So the definition is a ring R is a set together with two binary operations and we usually just denote them plus and times because, you know, because the integers are sort of the standard example to keep in your head, satisfying the following properties. So some people say closure explicitly, some people don't. I'll say it explicitly. If you say a set has an operation, you could consider it implicitly. It means that it's a well-defined operation, that if you apply the operation to two things in the set, it stays in the set, right? So like people don't always say this explicitly, but you could say something like this: A and B are in the ring, imply A plus B and A times B, which by the way, we also just write them, we just juxtapose A and B. We don't necessarily always write the dot in between or the time symbol or whatever. So that's your closure. That's why I'm calling that property 0, because some people don't say it explicitly. I guess I should say for all A and B. And so you also have for all A and B in the ring, A plus B equals B plus A, and A times B equals B times A. This is a commutative property of multiplication. Of addition and multiplication. Actually, I should say that not all rings, this is not always part of the definition. You'll see rings like matrix rings, for example. If you multiply two matrices, the order does matter. So some people talk about commutative rings versus non-commutative rings. In this course, we won't really ever look at non-commutative stuff, so we don't have to worry about it. So don't worry too much. I'm gonna just call everything a ring, even though probably you should say commutative ring. Some great handwriting there. Oh, okay. So yeah. So I'm going to assume our rings are commutative in the sense of the multiplication. Sort of addition's always considered commutative. It's kind of hard to come up with a ring with two operations that are both not commutative, or some sort of number system. But multiplication, definitely, when you get into more into higher math, it's not necessarily commutative. The multiplication is not commutative. Okay. So second property, for all A, B, and C in the ring, this is the associative property. If we do A plus B and then add C, it's the same thing as B plus C and then adding A. And A times BC. I should do it. I should match it. AB times C is A times BC. There are actually non-associative number systems, although those aren't usually called rings. Okay, so those are the first couple. The third is this is the only axiom that relates to two operations. So for all A, B, and C, we have that A times B plus C is AB plus AC. So this is the distributive property. Officially, it's distributivity of multiplication over addition. And it's important because otherwise there's no relationship between the two operations at all. Okay, then fourth is there exists an integer called 0 such that A plus 0 equals A for all A. Right, so there's a special integer called the additive, and it's the additive identity. Similarly, there's a multiplicative identity. And again, everything's inspired by the integers. So we call these 0 and 1 in general. When we just talk about rings in general, we call these 0 and 1 so that A times 1 equals A. You could also write 1 times A here if you wanted, especially because not all rings are necessarily commutative. Up here, we could have written equals 0 plus A also. Some people put that in a definition just for convenience sake. So this is the multiplicative identity. And then the last property is additive inverses. So for every A, there exists an integer called negative A. I mean, you know, again, there's some different ways to say this. You could just say there exists a B such that A plus B equals 0, which equals B plus A. And you could say we denote B by negative A. And so that's the additive inverses. I could have done something similar up here with 0 and 1. I could have said there's a special integer B so that A plus B equals A, and then we call that integer 0. But, you know, So it just depends on it's. I don't want to get too far into the weeds with the logic, but that's kind of the idea. So anything that satisfies these 6 properties, so 0 through 6, I guess it's 7 properties if you include closure, is called a ring. Okay. You've seen lots of examples. I said keep the integers in your head, but there's also the rational numbers, the real numbers, the complex numbers. You can add and multiply all of these things. There is the integers mod m, which we're going to call z mod mz. I'm going to talk about that in a video very soon, but it's the numbers 0 through m minus 1 with addition and multiplication mod m. For any m greater than 1, I guess, for any integer m greater than 1. You can, there's something we're going to see, for example, we're going to look at later in the semester, z adjoint I, which is everything of the form a plus bi, where a and b are integers and I squared is -1, so I is a, the imaginary unit. You can add and multiply things like this and get things that look like that, right? And it turns out they satisfy all these axioms. You could have matrices, n by n matrices, if you want to, actually with coefficients, with entries in a ring. If you allow if you take away the commutative property of multiplication. You could have lots of function rings, like rings where you like you could say something like the functions from the real numbers to the real numbers, where addition and multiplication are defined pointwise. Right, so f plus g of x is f of x plus g of x, and so on, etc. There's lots of examples. Anything where you have the 2 operations, most things that we look at that have sort of 2 operations, like an addition and a multiplication, are called a ring. A field, I want to talk about a field. This is another fancy term, but it's just something you've seen a lot. So a field, F, is a ring with the additional with the following additional property, basically multiplicative inverses. Additional property, which I guess I'll call property 7. So for every A in F, there exists a B in F such that AB equals BA. I'll just write it, AB equals 1. The multiplicative identity equals BA. So it's a 2-sided inverse. That's one thing that's important, especially when you have non-commutative rings. So, and I shouldn't say for all A. I should say for all A not equal to 0, because it's not true that we can invert 0, right? So if you throw in a multiplicative, if you throw in that every non-zero element has a multiplicative inverse, then that's called a field, and it's distinguished from a ring. And so we denote B. You could say 1 over A, but usually we write A to the -1 power. We denote this B, that is the inverse of A. And examples here, so the integers are not a field. Z is not, because, for example, 2 inverse is not an element of the integers. But Q and R and Z and C, sorry, the rationals, the reals, the complexes are all fields. Those are the standard ones. There's lots of other examples, but the main one that we're going to look at is actually called FP. It's really Z mod PZ, where P is a prime. It turns out, and we'll see this very soon, we haven't justified this yet, but very soon we'll see that every non-zero element in a field, sorry, mod P has a multiplicative inverse. So yeah, it turns out every non-zero element mod P has a multiplicative inverse. Okay, so it's just some terminology I want you guys to get used to. I'm just going to throw it around. It's just helpful to throw it around. And if you go on to take further math, you'll definitely see this a lot. Okay, I will stop this video here.